So in this video, we're going to talk about the kinematics of fronts. And what kinematics means basically is what is the flow going to do to basically temperature gradients. And so temperature gradients in the atmosphere are really the result of energy imbalances due to the differential heating of Earth on a large scale that then in ways get concentrated. And so we want to see what some of the mechanisms are that can lead to this concentration of temperature gradient, as well as trying to understand, are these the only mechanisms that can actually generate our fronts in a timely manner? And so we've been talking a lot about imbalances this semester, and the atmosphere can ultimately generate circulations from these imbalances in two primary forms, horizontal and vertical. And for the most part this semester, we've been concerned with our horizontal circulations, or our primary circulations, of mid-latitude cyclones. In previous classes in dynamics, you've talked about secondary circulations, primarily those related to jets, but we also have those secondary circulations related to fronts. And so we want to get at, how do we get a front, or what are the mechanisms within the atmosphere that can cause movement of air around to concentrate temperature gradient? And so the thing that we want to focus on is the magnitude of the temperature gradient, del T or del theta. And specifically, when we're thinking about changing the magnitude, we're thinking about the time rate of change. And so what we're really doing is we are considering, well, what is the total time rate of change of the magnitude on a pressure surface of our temperature gradient? And we can define this as F, where F is the frontogenesis rate. Now, one thing to consider, if F is greater than 0, that means the atmosphere is acting frontogenetically. If F is less than 0, the atmosphere is acting frontolytically. Now, what this doesn't mean is that if F is greater than 0, we're going to get a front, or if F is less than 0, we're going to get rid of a front. But primarily that the atmosphere is undergoing frontogenetic processes if F is greater than 0, or frontolytic processes if F is less than 0, meaning that the atmosphere is geared towards increasing the strength of the magnitude of our temperature gradient if F is greater than 0. And so it can help highlight regions that we want to watch for that may, in fact, develop a front. But it doesn't absolutely guarantee it. All right, so let's go ahead and first unpack this equation here that we have of F equals the total time rate of change of the magnitude of our temperature gradient. And we can do this in a more kind of complete horizontal version here. And that's where we're going to begin. Change a little color here for you. And so we're going to have F equaling our total time rate of change of the magnitude of our temperature gradient in the horizontal equals, and we're going to have, in the end, ultimately 4 different terms that we're going to talk about. And we're going to write it out here in the more complete 2-dimensional version, and then we're going to simplify it to 1 dimension to then consider these elements individually. And so to begin this equation, we have our gradient in theta, so basically 1 over our gradient in theta, times then our quantity of our couple of equations. Our first term minus the quantity, d theta dx squared, du dx, plus d theta dy squared dv dy. Term 1. Term 2 minus d theta dx d theta dy times the quantity dv dx plus du dy. Term 3 minus the quantity d theta dx d theta dp d omega dx plus d theta dy d theta dp d omega dy. And the last term plus d theta dx ddx of the quantity total d theta dt plus d theta dy ddy of their total d theta dt. All right, so here, our end bracket there. Here's our total Frontogenesis equation in 2 dimensions in the kinematic form. And so we have 4 different terms here that represent different things. This first term here, we can label as C. And really what we're talking about here is confluence. Our second term is related to shear. Our third term is related to tilting. And our last term is related to diabatic heating. And so let's unpack these just a little bit. In this first term, when we're talking about confluence, we basically see here du dx plus dv dy, modified by our gradients and temperature squared in the x and y direction. And so this is basically the wind pushing our temperature gradients together or apart as the result of confluence. In our second term here related to shear, we have this term dv dx plus du dy. Now that should look relatively familiar to you. It is close to vorticity, but it has a different sign. And so this is one of those deformation terms. And so what we're essentially seeing here is the effects of shear on our temperature gradients. In our third term here, tilting, we have the change in rising motion, d omega dx and d omega dy, such that we're taking our temperature gradients in the horizontal and the vertical and tilting them. And so that's changing the orientation of these lines, which is going to change the overall strength of the magnitude of our potential temperature gradient. Finally, our diabatic heating term here. Diabatic heating is what is outlined here in d theta dt. And so it's how is diabatic heating changing across our x or across our y direction, impacting, again, the strength of the magnitude of our temperature gradient. And so this term is great, but there's a lot going on here. And so we want to go ahead and bring this down to a more manageable level. And so we're going to basically look at this just in 1 dimension. And so let's go ahead first and draw out what we're going to want to assess through our modified equation. And so we're just going to draw a simple xy plot here. And we are going to consider that in this xy plot, we only have temperature gradients in 1 direction. And so here this might be theta, below it theta plus delta theta, and above it theta minus delta theta. So kind of a typical northern hemispheric setup. And the only place we have a gradient is in the y direction, right? We have our temperature changing as we go to the north or to the south. And if we're in the east-west direction here, our theta lines are exactly east to west, and so we don't get any change in the east to west direction. So we can take that full 2D equation that we had above and modify it and have all four terms, but in only this one direction. So what we want to do now is we want to consider the total time rate of change of our temperature gradient in the y direction. Here we're using minus d theta dy to kind of signify going north correctly. And so we're now going to have only parts of those terms we had above. And so let's go ahead and start with our confluence term. Our confluence term now would be dv dy times d theta dy. And this would be our confluence term. Our shear term would be plus du dy d theta dx. And that would be our shear term. Our third term would be our tilting term, d omega dy times d theta dp. And this was our tilting term. And finally, we'll have our diabatic term, minus d dy of d theta dt. And this was our diabatic. And so what we're going to want to do is to now assess how are these four terms, confluence, shear, tilting, and diabatic processes, going to affect situations that look like this image that we drew here. And we're going to look at each one of these terms in a future video. And so this is the basic construct through which we can understand the kinematic forces revolving around generations of fronts. And so in our kinematic version here, we have confluence that can impact it, shear that can impact it, tilting, and diabatic processes. Thanks for watching.